Okay, let's talk about how electrons can change what are called energy levels and the amount of energy that's emitted or absorbed when an electron does that. Okay, so let's pretend here's the nucleus. And then I just drew 6 rings around here. We'll pretend each of these rings represents an energy level. So let's say in the first situation, the electron is in the 1, 2, 3rd energy level. So the energy level is abbreviated lowercase n. Sometimes it's called the shell. It's like how many energy levels is it away from the nucleus. So here we would say n equals 3 because it's in the 3rd energy level. 1, 2, 3. So the question is going to say how much energy is emitted when an electron undergoes a transition from n equals 6 to n equals 3. So let's say here this is 1, 2, 3, 4, 5, 6, n equals 6 right here. So let me just write out the question. What is the energy and wavelength when the electron undergoes transition from energy level 6, n equals 6, to energy level 3, n equals 3. So there's a few key words here. So energy is going to be emitted because we're going from a higher energy level to a lower energy level. If we were doing the opposite, if we were going from low to high, that would mean energy is being absorbed. So that's a key thing to pay attention to. When energy is emitted, that means energy is being released. That means the change in energy overall is going to be negative. So this triangle sign here means change in. So the change in energy, we can't measure the absolute value of the energy, but we can measure the change in energy from 6 to 3. So it's going to be emitted. It's going to be a negative number. So we're going to get to all of that. So what is the energy and the wavelength? So we just do one thing at a time. Let's solve for energy first. Once we know energy, then we can solve for wavelength. Okay, what is the energy emitted? So the formula that we use to calculate the change in energy when an electron transitions from one energy level to another is change in energy equals the negative, what's called the Rydberg constant. And why this H is here is because this is only for hydrogen atoms. So electrons, or this is just talking about the element for hydrogen. That's all we'll ever talk about. So this is the Rydberg constant, is what this R stands for. 1 over NF2, this is the final energy level, minus 1 over Ni squared. I don't know, I think I said 2, I meant squared. NF squared minus Ni squared. And Ni, this is the initial energy level. You may see other versions of this equation if you were to look it up somewhere else where it would say N1 squared or N2 squared minus N1 squared. So you can use 1 and 2 for initial and final, or you can use I and F for initial and final. Either are the same thing, it doesn't matter. So the Rydberg constant, again, all these constants will always be given to you. You're never memorizing constants. But the Rydberg constant is 2.179 times 10 to the negative 18th joules. So change in energy equals negative Rydberg constant times 1 over the final energy level squared. So what is the final energy level? So it's undergoing a transition from n equals 6 to n equals 3. So this is the final energy level. It's going from 6 to 3. So the final energy level is 3. The initial energy level that we're starting with is 6. So now I'm going to write out what I have. So change in energy equals negative Rydberg constant, negative 2.179 times 10 to the negative 18th joules times 1 over nf squared. So 3 squared. 3 squared is 9 minus 1 over the initial energy level squared. 6 squared. 6 squared is 36. So if I take 1 over 9 minus 1 over 36, and then I multiply it by 2.179 times 10 to the negative 18th, I get a change in energy of negative 1.816 times 10 to the negative 19th joules. That's the change in energy. And again, this sign, it's negative because we're going from a high energy level to a lower energy level. From high to low. Also, it tells you light is being emitted. So this change in energy, it's being given off. There was no significant figures in this problem because n, 6 and 3, these are counted numbers, so they don't contribute to the number of significant figures. So any number of significant figures would be correct because this has no significant figures either because it's a constant. I just used 4 because there were 4 in the constant. Okay, so that was the first part of the problem. It asked for energy. The second part of the problem asked what was the wavelength. So now this is part 2 of the problem. Part 2, solve for wavelength using energy. So what is the wavelength using this change in energy that we just solved for? So now I'm going to say energy equals, and I'm not going to use this sign because this sign, this negative number, it just tells me the direction of the energy. It's the change in energy. It means this much energy is being emitted, but it's not an actual negative number. The value of the energy is the absolute value of this number. So the energy is 1.816 times 10 to the negative 19th joules. So I'm solving for wavelength. So the formula that we just used says energy equals Planck's constant times frequency. So the first thing I'm going to need to do, I'm solving for wavelength. 1, I'm going to use the energy equation to solve for frequency. Then I will use the frequency and the speed of light to solve for wavelength. I'm going to say solve for wavelength in nanometers because that's the way that we always see wavelength reported. If I don't specify wavelength distance, you could say anything. Probably always in SmartWorks there'll be a blank and then it will say nanometers after that, so we should just get in the habit of doing that. Okay, so first let's use the energy equation to solve for frequency. So that's what I'm going to do here. Energy equals Planck's constant times frequency. So that means I'm going to divide both sides by Planck's constant to get the frequency. Frequency equals energy divided by Planck's constant. So energy 1.816 times 10 to the negative 19th joules. Again, I'm not using the negative sign here because the negative sign is just showing the direction of the energy, that energy is being emitted. If we were going in the opposite direction, that amount of energy would be absorbed. So the sign only shows us the way the direction moves. It doesn't mean that there's a negative amount of energy. So that's why there's no negative sign here. Divided by Planck's constant, 6.626 times 10 to the negative 34th joules per second. So 1.816 times 10 to the negative 19th divided by 6.626 times 10 to the negative 34th equals a frequency of I'm just going to go with 4 significant figures because that's what we have here, 2.741 times 10 to the 14th 1 over seconds. So this is my frequency. So frequency equals this. So now I'm going to use the frequency and the speed of light to solve for wavelength. Let's do that one in a different color. So remember the equation that we use to solve for wavelength using frequency is the speed of light equals the speed of light equals wavelength times frequency. I want to solve for wavelength, so I'm going to divide both sides by frequency. So wavelength equals speed of light divided by frequency. So the speed of light is 2.998 times 10 to the 8th meters per second. And the frequency we just solved for to be 2.741 times 10 to the 14th, 1 over seconds. 2.998 times 10 to the 8th divided by 2.741 times 10 to the 14th. This gives me a wavelength of 1.094 times 10 to the negative 6th meters, because seconds cancel. So let's go ahead and convert that to nanometers. I'll do that down here at the bottom. 1.094 times 10 to the negative 6 meters. And there are 1 meter is 1 times 10 to the 9th nanometers. So I'm going to take that number times 1 times 10 to the 9th. And we get a wavelength of 1094 nanometers. So that's kind of a more complicated problem. Anytime I can ask a question on an exam where it includes multiple steps, multiple parts of information, I like to do that. So this problem right here includes 3 different processes that we've worked through now. So we used the Rydberg equation to solve for the amount of energy change, and then we were asked to solve for wavelength. First, we had to use Planck's constant to solve for frequency, and then we used the frequency to solve for the wavelength. So it used all the equations that we've talked about so far. So this is an example of a question that you should be prepared for on an exam. Certainly doing each of these steps individually, making sure that the math is right, the significant figures are right, and the unit is right.